All right, guys, so this lecture 7.4, section 7.4 about vectors, operation, and the dot product. So what's the big idea? The big idea is the vector are mathematical identity that represent both a magnitude and a direction. And the big skill that you should be able to add vectors, convert between their two representations, and find the angle between two vectors. So a vector is the name given to an object meant to represent the length, also called magnitude, and a direction. So, different vocabulary, the line segment pointing from the point 1, 1 to the point 3, 3. You have an initial point, a terminal point, okay? Initial point right here, terminal point. Initial point is right there, and the terminal point is right here. I'll let you read all of this. Pretty simple, pretty straightforward. How do we calculate the length of a vector when it is represented in a Cartesian system coordinate? Use the Pythagorean theorem. You know the length of this side right here, which is 2. You know the length of this side right there, which is also 2. Well, it's pretty easy to calculate the length of the hypotenuse, which is the length of your vector A, which is the magnitude of your vector A, and its square root of 8 equals 2 square root of 2 at the end of the day. How to represent and how to write the magnitude? We can represent the magnitude by having 2 this way right here, or without the little arrow above, and so you end up to have just A equal 2 square root of 2. So let's move on. On this second example, you need to understand that a vector is defined by two components, a vertical component, AY, and an horizontal component, AX. Okay? And when you express your vector, you always express the horizontal component and then the vertical component. All right? So if you have a vector defined this way, that means you have a vector made of 2 times the vector x. And what is x? X is the vector purely in x dimension, and the magnitude is 1, so it's just to define that we're going in one direction, okay? And 2 times y, because it's also 2 on the y component. Now, let's try to practice a little bit. And what do we have right here? So basically, we suppose you follow a vector A, magnitude 110 miles at 20 degrees, and the follow a vector B, 220 miles at 225 degrees. Okay, so remember, to have 225 degrees, what we did is from this point right here, we went 225 degrees. Okay, now that said, let me erase this 225 degrees to make sure that we do understand and it's not too much on my drawing. I have finally A plus B, and A plus B is defined by the resultant vector defined by an original initial point, and it's coming from here and it's going down up to there, right there. All right, so what I can write pretty nicely is that the resultant R is equal to A plus B. Okay? So, you know what? Let me keep that. I decided to keep it. You know, here we go, right there, 225 degrees. Why not keeping it? I know that A, which is equal to A, equal 110. I know that B, why do I double? Equal 220. So what is the distance? What is the distance? Well, I can use my quadratic, quadratic, oh my goodness, my Pythagorean theorem, you know, because I can easily go over here and I can easily define that R as the resultant R as a magnitude equal to 125 miles at 240 degrees. Okay, and to define 240 degrees, 240 degrees is right here. All right. Let's say it's kind of almost there. It's a little bit bigger than 225, so roughly that's 240 degrees. So if I defined R, I can also define R as the horizontal, as an horizontal component plus a vertical component, okay? And what is the value of this horizontal component Rx? Well, the horizontal Rx is the sum of the horizontal component on A plus the horizontal component on B. So actually I just want to respect, so I'm going to use my B. It's in red, so I'm going to use my red right here. Just rewrite that in red. So I'm going to have plus bx, and it's equal to ax plus bx, and therefore I'm going to have 103.4 miles plus negative 155.6 miles. Why do I have bx equal negative? Because if you look at the bx is right here. Okay, bx, this is bx. And bx is going in the opposite direction as the vector, which is, like we said before, just to show you again, the vector purely in x dimension with a magnitude equal 1 and going in one direction. And I know that it's going to the left, so obviously that's why we have negative 155.6 mile. So we end up to have a Rx equal to negative 52.2 mile. And that means my Rx is going to go in the other direction than the purely in x dimension vector. So do we have that? Well, yes, because if you look at it, Rx is right here. This is Rx right there, right here. Right here, we're having Rx, and Rx is going in the opposite direction of the vector purely in the x dimension. Now, if I do the same thing for Ry, I can expect to have Ry being negative. So Ry equal to Ay, and let me use the same color, Ay plus By, and we end up to have 37.6 plus negative 155.6 mile, By equal Bx, and so we end up to have a value of Ry equal negative 118.0 mile. Okay. Therefore, I can easily express R as negative 52.2, negative 118.0. All right, guys. So let's jump on the next problem. So state an approximate value of a plus b plus c given that a equals 4 at 45, b equals 3 at 180, and then c equals 330, equals 6 at 330. Well, when you graph this vector, respecting the magnitude of each vector and the angle, you will end up to have r around 3 times, actually I'm going to get rid of this because I don't need to have that, equal 3, and it will be at 340 degrees. To add vector mathematically, we add like component, because we can get from the first initial point to the last terminal point by moving in the x and the y directions only. You will notice also that this expression y here and this expression y there work even if the angle theta is greater than 90 degrees. Work even if theta is greater than 90 degrees. Okay? All right. Let's finish for this practice, to do the practice, and then you will have a second video because unfortunately it's going to take me more time. So what do we have right here? We're having the vector A, and the vector A, x, is defined as the magnitude of the vector A cosinus of the angle theta, because if you look at the cosinus of the angle theta, and cosinus of the angle theta is right here, so we're having right here ax, and we're having right there ay, cosinus theta equal ax divided by a. So therefore, by substituting the value, we end up to have ax equal 103.4 miles. Now, if I look at ay, so ay equal a sinus theta, because I know that sinus theta equal ay divided by a, the opposite side divided by the hypotenuse, and therefore I end up to have ay equal 37.6 when I substitute the magnitude of a and the angle theta equal 20 degrees. Now I can do exactly the same thing for bx. So if I look at bx this time, well, same idea, cosinus of the angle theta equal bx divided by b, so bx equal b times cosinus of the angle theta. I substitute the value of b and the angle theta, and I end up to have a value of bx equal negative 155.6 miles. The sign is even correct. Okay, the sign is correct, because I know that bx is going to the opposite direction of the vector right here, x, all right, magnitude 1, which is purely in an x dimension. If I look at for the sinus, I end up to have by, sinus of theta equal by over b, and so I end up to have by equal b sinus of the angle theta, and you will find a value of by equal to negative 155.6 miles. Okay, so I think we're pretty good now. I'm not going to move on. I'm going to let you finish to copy that. You should be able to be finished right here. But I'm going to, for exceptionally, have a second video, because unfortunately I can't cover this section in only one video, but that's not too bad, right? You pretty much had only one video 95% of the time, which is pretty good. So I will see you in class, and work very hard, and you will see everything, it will be okay.